So now let's say if there are multiple wire, because here is another most important part is there, that is net. Net means the total current. Let's say there are more than one wire, like this is any circular loop. Here is I1, it is I2, like this is I3. So if like it is like this, multiple wires are there, then it will be B dot dl, it will be mu naught total I, and total I will be I1 plus I2 plus I3, the total current we have to consider. But mind it, here we have to also keep in mind the direction of I, because this I2 is in opposite direction, so it will be actually minus I2. So this is the total current, I1 minus I2 plus I3. So these two words are very important, net current and the enclosed by the closed path. Okay, so if there are many wire like this, let's say like this, there are n number of wires are there, let's say, then it will be B dl equals to, in each wire the current is I, so it will be Ni. Okay, so this is the significance of our Ampere's circuital law. I think Ampere's circuital law is now clear. In next part we will start the displacement current. This displacement current is essentially significance of the Ampere's circuital law, because in Ampere's circuital law, okay, we are considering a wire. In that wire the electric current is flowing, but that electric current is a constant current. If there is a change in the current with time, then what will be that line or path integral? That is not clear in the Ampere's displacement law. Means, let's say this is a current I and this is a loop. This di dt is actually 0, right? We are not considering that di dt is 0. But if there is a change, electric current which is changing with respect to time, or let's say if there is a electrical flux which is also changing with the electrical flux, means that electric field is changing with the time, then this B dot dl, that line integral, will not be equals to mu naught I. Okay, so then we have to make a correction. Maxwell did this correction. Maxwell add a term in that equation, Ampere's law, and that is a most general law which essentially covers all the cases where the electric field is constant, or whether the electric field is changing with the time, or there is a changing electrical flux. For each and every case we can generalize this law. So what is that? B dot dl is mu naught I was there, he added one more term which is Id. This is called the displacement current. This Id is termed as displacement current. So what is the form of this Id? Okay, so as I said that if we consider a electric field which is changing with respect to time, that means there is an electrical flux. So electrical flux which is changing with the time. Okay, so what is the electrical flux? Electric flux, this is phi E. Okay, and this Id is this displacement current is Id equals to epsilon naught into d phi dt. Okay, we can see from our physical understanding that if there is no electrical flux which is changing with respect to time, that means there is a constant electric field, then this part d phi dt is essentially 0. this should be 0 for this case. So, then we can say that it will be Ampere's law. But if there is an electrical field which is changing with respect to time, then the electrical flux that will be also changed with respect to time, then d phi dt will not be 0, and in that case there will be a non-zero displacement current, and we have to account that, and for accounting that displacement current we have to use the general law, which is, this law is called Ampere-Maxwell law. Okay. So, this is for okay, this is the electric flux. Now, we have to understand this part. Let us say we are taking two capacity. In general we have to write it first. In general we can write it B dot dl equals to mu naught I plus mu naught epsilon naught. Epsilon naught is the permittivity of that vacuum, d phi E dt. Okay, this is Ampere-Maxwell law. What is phi? Phi is the electrical flux, and the form of the phi is integration. What is that? This is the surface. Let us say there is a surface. Let us say it is a sphere. So, in case of sphere there is a surface, and that surface is S surface, and let us say the electric any area, this is the dA. So, this dA is acting like this, and the electric field is present like this. Then E dot dA is the dot product between that E vector and the dA vector, and if we integrate over the all surface, this is only the ds part, this is the ds part. If we integrate over all surface, then we obtain the total electrical flux. We can understand this. I am not getting into in detail in this. This is actually the surface integral. In surface integral, this is for ds. Ds, it is clear that E dot dA is the electrical flux. Now, if we integrate over all surface, then we obtain the total flux. So, we can actually write like this: phi E equals to S. This is the d phi. So, then it is clear, right? Okay. So, I am not getting into that, but the definition of the phi is this. Okay. So, now it will be, if we consider two capacitor, let us say, I have to draw first. This is a capacitor plate. There are two parallel capacitor plates, right? We are considering. This is another one. Two parallel capacitor plates, and electric current is flowing like this. I is the electric current, and now we are considering a surface like this. Okay. Okay, charge in this plate is minus q, here it is plus q. So, electric field will be present along this direction. So, this is the electric field, which is E, and the area of that capacitor plate is A. Okay. So, this surface is S1 surface, and this part, okay, no. Okay, and this surface is S2 surface. Okay. So, then what will be the phi, the flux between two capacitor plates? We know that E, the electric field will be, let us say we are not using the vector sign, if it is E, then it will be phi is not phi, it's sorry, q is the total charge, this is the q, divided by area and permittivity. Here we are considering vacuum, that's why we are writing the permittivity of the vacuum epsilon naught. So E is Q time Q divided by epsilon naught A. So then we can write E dot epsilon naught is Q by A, or we can also write that yes EA. Okay. So now from here we know that phi is integral of epsilon dot E electric field and dot product of electric field and the area vector. Then we have to take the in total surface integral. Okay. So now here electric field we can take it out E, and okay, let me do part by part. So we can write here this is E dA cos theta. What is the theta? The area vector also along this direction, right, parallel to the electric field. So it will be theta is 0, so cos 0 is 1. So we can write EDA. Okay, so it is actually EA, right, and EA we know here from Q by epsilon naught. So for these capacitor plates, the phi becomes, the electrical flux is Q divided by epsilon naught. This is electrical flux. So now if we input this part here, then we obtain that what is the ID, then ID will be epsilon naught 1 by epsilon naught dq dt. So it is actually dq dt. That means, what does it mean? It means that the electric current changing with the time, means that dq is the charge, the electric charge is changing with the time. That is the definition of the current. That's why it's the displacement current. So essentially the change of the the electrical flux with time is essentially governs the current changing, the electrical charge changing with the time, the current actually. That's why it is the displacement current. Okay. So in general we can write this. So what we obtain, that first E dot dA, that is equals to phi, right, that is equals to phi for surface. Second thing is what we that B dot dl generalized form. Okay, we discussed no line integral. This is the line integral B dot dl. If it is a for P to Q, it is PQ. If it is not, if it is a closed path, then it will be circular. This is the line integral, right? And in case of surface integral, it is why it is line integral? Because this element is a line element, small line element. If it is surface element area, then it will be not for B, for any vector. We should not write B here. For any vector A, let's say here any vector V vector, it is, if it is dA, if it is over total surface, then it is called surface integral. So for this law, first law is for the surface integral and this is the line integral. Okay. So this is the actually first law of the Maxwell law, first law. This is one of the law. It is not first, second, third. There are four Maxwell equation, not law. So this is one of the equation. So now B dot dl, what? Okay, what was the form of B dot dl? It was actually mu naught I plus mu naught epsilon naught d phi e dt. Okay. So what does it mean? What is the physical significance of this mathematical expression? Actually, this expression means that the main point of this law is the magnetic field can be produced. Magnetic field can be essentially produced in two ways. If current, one of the form is if current flows, this is two parts are there, na? This is one part, this is another part. This part, if we focus in this part, then current flows through if current flows, there will be a non-zero I. Then magnetic field will be produced because it will be non-zero. And the second part is if there is a electrical flux or electric field which is changing with time, then also the magnetic field will be produced. So from this law we can say that magnetic field, why I am saying that, because B dot dl is 0, it means that B is 0. Okay, so there is no magnetic field. Now magnetic field, we can okay, we can understand. This is I, here B dot dl is non-zero, right? If we take any loop, there is no current carrying wire enclosed by that loop, then obviously B dot dl will be 0. What does it mean? It means that there is no magnetic field present. So, but if we input a current carrying wire inside that loop, then what happens? There will be a non-zero magnetic field, and that non-zero magnetic field will make that line integral non-zero, which means that current carrying wire, the electric current which is flowing through that wire is creating a magnetic field around that wire, which make this line integral non-zero. If there is no current carrying wire, then there will be no magnetic field produced. Okay, so we can write the magnetic field can be produced. There are two ways. First is, as I discussed now, current flows through a wire. Let us say conduct. And the second part, from this part, we can say that if there is no current carrying wire, then also there will be a magnetic field. The magnetic field can be generated. How? If there is a electrical flux which is changing with time, means that the electric flux means the electric field, because the form of the electric flux is EA, right? Or in general that surface integral of E dot dA. So if there is an electric field, then there will be electric flux. So if there is a electric flux which is changing with respect to time, means that there is an electric field which is changing with respect to time. In that case also there will be a non-zero B dot dl. So the second point is that electric field which is varies with time in a region. Okay, so this is the second part, the second condition for the non-zero magnetic field. Okay, so we can again we can similarly write the generalized Faraday's equation, which is E dot dl, the line integral of electric field, it will be minus d phi e dt. Again this d phi e is the, phi is the electric flux and d phi dt is the electric flux which is changing with respect to time. This is the Faraday's law. This is, first one is the Gauss law. Let me write it. I don't know the spelling is correct or not. This is the Gauss law for electric field. This is Ampere Maxwell law. This one is the, I will make a list, and this is the Faraday's law. Faraday, which is Faraday's law. Okay, so there is another Gauss law for the magnetic field, and that is B dot dA is 0. Okay, so what is the significance of the last two laws? First one is that this is also the line integral, right? So for the line integral of a electric field E dot dl, it will be equals to the change of the electrical flux with respect to time, and it's equated with a minus sign. This means also that if there is a electric electric field is changing with respect to time, obviously there will be a electrical flux is changing with the time, there will be also electric field. Okay, so this is the third law. So similarly we can conclude that a changing magnetic field creates an electric field, and also here we can, from here we can see the changing electric field is creating a magnetic field, and similarly changing magnetic field also can create a electric field. How? Because if d phi dt is there, that means that is a, okay, phi b is the magnetic flux. So now we can relate that these 2 and 3. So these are the 4 Maxwell's law I will discuss in next part of my talk, that I will discuss in detail that 4 Maxwell's equations. Essentially these are the 4 Maxwell equations. I will come into that. 4 Maxwell's equations. Okay, thank you.